Florida living operates on a harsh mathematical ratio. Enjoying 350 days of ideal coastal weather requires uncompromising preparation for 15 days of extreme cyclonic volatility. When a Category 3 or higher hurricane makes landfall, the primary residential infrastructure often fails. The power grid goes offline, and the water supply can be compromised for weeks. This timeline plots a major storm's 3 phases. Phases 1 and 2 cover preparation and the eye, testing structural integrity against sustained gusts and flying debris. Phase 3 is the prolonged aftermath. Without power, homes trap intense heat, while floodwater breeds mosquito swarms. Maintaining a shaded, ventilated, and bug-free environment through the screen enclosure preserves post-storm livability when the interior of the house becomes an oven. An enclosure survives these extremes through strict mathematical compliance with the Florida Building Code, exact metallurgical selection at the fastener level, and dynamic wind load management. To understand this science, we must look past the pristine finish of a completed structure and systematically peel back its layers to examine its engineered anatomy. The structure survives through a heavily regulated, meticulously calculated defense system, despite a physical composition that is mostly empty space. Look at this split view comparing a structural blueprint to a finished pool enclosure. The theoretical design limits of the engineering schematic map directly into the physical aluminum framing that holds the space together. This slide compares the rules governing construction. Standard geometries use the AAF guide's prescriptive methods without a custom engineer. But the custom standard on the right shows that high-velocity hurricane zones or complex architecture require a licensed engineer under Florida Building Code Section 2002. If a design integrates into a multi-story roofline or features massive clear spans, it mandates specific, rigorous wind load calculations produced by a licensed engineer. To meet code, roof panels must resist ASCE 722 component and cladding wind loads, calculating exact uplift pressures. Engineers must also evaluate ponding and stability, ensuring flat spans are rigid enough to support the dead weight of rapidly accumulating rainwater without collapsing. The macroscopic aluminum skeleton is entirely constrained by these equations, ensuring the frame won't buckle under simultaneous hurricane winds and torrential rain. A solid surface absorbs the total kinetic force of a wind gust, taking on the full pressure load. A porous mesh grid diffuses that energy, allowing the velocity to pass safely through. Screen enclosures frequently incorporate solid lower panels for privacy or to act as splash guards. But in a cyclonic event, those solid surfaces become a severe aerodynamic liability. This graphic highlights a strict code mandate from FBC Residential R301.2.1.1.1.1, created specifically to mitigate that exact vulnerability. The code dictates that any solid panels made of vinyl, tempered glass, and acrylic integrated into a screen enclosure must be engineered to be physically removable. The mandate also requires a permanent identification decal on every temporary panel to ensure the homeowner understands their operational duty. The rule is absolute. These specific panels must be physically removed from the structure when wind speeds are projected to exceed 75 miles per hour. Temporarily stripping the solid surface area from the frame acts as a dynamic pressure relief valve. It allows the air to flow cleanly through the mesh, preventing the entire aluminum skeleton from acting like a sail and tearing itself off the concrete foundation. A perfectly engineered aluminum frame fails if its microscopic connection points decay. When chloride ions hit standard hardware, they immediately begin dissolving the metal. A fastener corrosion study led by Dr. Curtis R. Gurley at the University of Florida identified a specific failure point. Catastrophic collapses rarely start with heavy aluminum beams. They begin with the microscopic degradation of the fasteners holding those beams together. Coastal air is heavily saturated with airborne salt. This chloride-rich atmospheric chemistry rapidly accelerates corrosion on standard metals. The fastener metallurgy matrix compares hardware. Electro-galvanized screws carry a high risk of degradation. Ceramic-coated stainless steel risks galvanic corrosion if the coating peels. However, hot-dipped galvanized fasteners are the benchmark, offering superior resistance and a remarkably low unlike metal reaction risk. Metallurgy dictates the lifespan of the entire build. An over-engineered, perfectly compliant aluminum frame will collapse in the first severe storm if its joints have quietly dissolved in the salt air. The skin of the enclosure requires equal scrutiny. Standard fiberglass window screens tear under mild pressure and degrade quickly. Coastal defense requires a heavy-duty industrial mesh material. These screens utilize a core of high-tensile polyester, heavily coated in protective vinyl, sold commercially as tough screen or pet screen. This exact material composition can withstand a Mullen bursting strength of up to 538 pounds per square inch, providing a massive physical barrier against localized flying debris. For open walls, this schematic outlines the Somfy RTS motorization system. It allows massive screen spans to roll up or down seamlessly. This movement is controlled by weatherproof universal receivers communicating with remote wind and UV sensors that continuously analyze environmental loads. Integrating high-tensile vinyl-coated cladding with these autonomous environmental sensors results in a fully active, responsive climate control mechanism for your home. This Venn diagram summarizes a properly engineered build: structural code, advanced craft, and aesthetic comfort. Mastering ASCE 722 load limits, hot-dipped fasteners, and high-burst cladding creates a space that looks elegant on a sunny day, but performs like a fortress during a Category 3 storm. The physical thickness of aluminum beams means nothing if the microscopic joints holding them together fail. Strictly controlling materials at the microscopic level and dynamically managing wind loads allows these structures to function as generation-lasting coastal defense infrastructure.